Good afternoon, all. Thank you, everyone, for being part of this session. Today, I am presenting about the fitness for service of oil and gas components based on the level 3 assessment, that is by numerical method. Basically, fitness for services, it's an ability to demonstrate and structural integrity of an in-service component consists of flaw or damage. If you see the background, in early 90s, their joint industry project, they have started the fitness for service guidelines for refining industries in 2000. They have started with the joint venture with ASME. The APA have released the 579 general practice code with coordinate for both, which welcome for both refining and non-refining industries. In 2007, when ASME joins forces with APA, they are released with ASME FFS1 and APA 5791. So in 16th edition was started. So if you see in the industries, generally normal many components which will having a certain life, life or during the operation. In those components, some of the components will they when used for various specification based on the applications, they will give continuous service. Some of the components will fail due to irrespective of any of the reasons. These failures we have divided into a number of levels, like level 1 with the more conservative method, level 2 and level 3 with the most rigorous method. That has to be these are the levels we have taken with the rigorous method. Now, as there is a various technology has to be improved, the numerical method has being a more productive and the more challenging the technical by overcoming the many empirical evaluation, empirical method with the, and also the analytical methods. So with this inspection as the final outcome, we can take a decision where the component can be run as is, or it can be repaired, recheck, or take a alert, or retire the equipment. So I will take out some of the examples where we have executed and provided the engineering solutions for the fitness for services for oil and gas equipments with respect to the level 3 assessment. So just non-disclosure policy with our clients. I am representing the equivalent model over here. If you see the first example, the autoclave reactor vessel, based upon the application, this will be keep on the process different changes. Say usually they will use for the to accurate the control over the temperature and pressure to achieve the desirable chemical reaction, and so like this based on the application. Here we found the problem is there is a crack was initiated at the nozzle junction, where that was the problem we found. Then how to bring that mathematical problem to our in the actual scenario, the physical model to the mathematical, that was the challenge. We collected the data from the asset integrity team. We built a CAD model. Many of you know the general procedure for the FEA, no need to repeat full procedure. So we have the, once we building the with the taking care of the weld joints and the nozzles with the shell, with the corrosion and all, we have applied the applicable process pressure and boundary condition. Then the challenges, because the more challenging part over here is, as we know, the temperature when it's come into the picture, the whole scenario of the material will keep on changing, the allowable will keep on changing. So from the room temperature, ambient temperature, the allowable is different. When it goes to the higher temperature, the allowable is different. So then we, after executing from the solution, we found the life of the component would not be adequate with the desired life. The requirement around 45,000 cycles, where it comes less than 20,000 cycles. So we have given our judgment with the where we can customer take the benefit over here. We can that can be replace the component, it can be repaired. So move to the second example is vertical heat exchanger. You can see the cooling effect circulation system. We can the overall vertical having different application, horizontal shell type heat exchanger have different application. If you see the example with only the outer shell of the part, here if the more challenging part what we have observed is, it is over the support ring part, the overall environmental, due to environmental chemical reaction, the 360 degree of the component was fully corroded. when the nominal thickness is around 27 mm, the asset integrity team, we have captured the data in such a way that the grid wise, overall 360 degree, the grid wise we have measured the data along what will be the thickness. If you see the west side, it was 7 mm depth already corroded, somewhere it was 12 mm, somewhere it is 8 mm. So how do I bring that physical model to the actual mathematical model in the numerical method? That is the most challenging. By capturing the each grid, bring the cell with the what is the remaining thickness of the corrosion, remaining thickness of the shell over the ring support. So these are the part we capture one by one. Again, the temperature as what it was in respect to 350 degrees Celsius. Then we checked with the structural integrity first, whether this thickness will be enough to take to run the safety operation. Then that was coming at the west side, it has to be repaired immediately. That the client was stop the operation. Then we have suggested for the customer that benefit customer taken by that has to be repaired immediately for that. So moving to the third example, it's a cooling catalyst receiver. It is a part of the fluid catalytic cracking unit, where it can be receives the catalyst from the catalyst, and it will separate hydrocarbons which are attached to the catalyst. Here it's not purely for the it is still what it was in fabrication stage, not yet installed at the site. It is not purely with the fitness for service, checking with the structural integrity, where we have the one challenge is where there is a cooling effect, sudden drop from the temperature 600 to 250 with a span of time. The capturing of the transient timeline also, that is the where the simulation effects has to be taken care only. We have to apply the true stress strain curve. The data will be received from elastic plastic engineering stress strain that has to be converted, because it has to capture instantaneous overall area for the true stress strain. If you go with engineering, then omit with the wrong results. Then that the challenges we faced, and we have come up with the solution. The entire system, the vessel was safe, but only at the support structure we made it as the life of the support structure, the supporting lug where 2 lugs were there, that is not within the desirable life. Then we made the changes for the support structure that has to be moved to the next. We have improvised the design of the support structure. Then we have come up with the new solution for the our customer. Then it has to be remodify the support structure, and then went for the fabrication. So similar way with the few examples just we have bringing over here. One is above ground the water storage tank, the where the we want to the proposed to increase the water capacity by 75 kiloliter with the existing tank. First we checked with the what is the structural integrity for as is condition, how the thickness behavior from the coarse one bottom to the top due to the hydrostatic pressure that is effective most for the tanks. We have found that it has to be increased with certain height, then we can come up the overall solution with the required output. So similar way, if the weldolite defects we can see at the center middle one, where it can be in the during the NDT, we collected the data from the NDT test. They found a flaw at the weld region. This weldolates, socolates, or some other where it had be used for the stress concentration region. Over there they will keep a sample probes, thermowells, whatever be with the sensors for the measurement data. So they have found a defect over there. Then that has to be data taken by NDT. We have captured the model. Then we have see the process flow, the drag force, the lift force applied all the loads. Then check the life of this, it can be run or not. Then suggested it has to be repaired immediately. So similar way, one is heat exchanger channel assessment, where they want to measure the thickness. Due to the running condition, the thickness has to be eroded. We have to capture the, as you come up with the what the analysis challenges here it goes with the elastic plastic analysis. Again the material data behavior will be completely changed. Yeah, okay, that's all. So that's all be capturing the, we have to check with the triaxial plastic strain data that has to be taken, and that we have to compare with the equivalent plastic strain from the simulation. The allowable it has to be in the same range, within the range. Let's summarize with the examples. The first example, in autoclave reactor vessel, we recommended to replace the equipment and change the process parameter just to save the safe reaction for new one. In vertical heat exchanger, repair the west side portion and strengthen the part. In catalyst vessel, we change the design of the, we modify the support structure design. So some of the cases I have presented in some of posters. We can during the tea break we can go through that. And if you have any queries, please feel free to contact me. So this is with the data captured by asset integrity. The life after prediction. This is we have shown with the finite element analysis. The life, integrity part, the life we can show whether the stresses are within the allowable, like membrane plus bending at the weld junction. Okay. So based on that, we can give the data captured. We can give the life this much you can run for this number of cycles. Yeah.
We'll take it later. Sorry, because we are short of time. We'll take the questions later. We'll just take it after the other presenters.
Thank you.
We'll have time for discussion. We'll take it up then.